Okay? All right. So today we want to talk about limits involving infinity. We talked about that a little bit yesterday, showing that the limit as x approaches infinity, and the limit as x approaches negative infinity, going to the extremes, that limit will give me what is known as my horizontal asymptotes. All right? My graph can cross a horizontal asymptote near the center, but at the extremes, it will not cross the asymptotes at the extremes. If I have a 0 on a horizontal asymptote, that means it's going to cross that asymptote. If I don't have a 0 on the asymptote, then it will not cross. So keep that in mind. We talked about left hand and right hand limits at the vertical asymptotes. At the vertical asymptotes, my limits will always be what? All right, they'll be opposite, correct? Except when I have a even multiplicity, then they will be the same. So we want to keep that in mind. In behavior models is what we didn't talk about yesterday. In behavior models. In behavior models is basically talking about what does my graph look like at the end. At the end. So a lot of times, if I get a graph that looks something like this, and I just look at that part close up, it looks like a straight line. It doesn't look like a curve anymore. But what happens is that a lot of my oblique asymptotes, say for instance if I have this asymptote and this asymptote. A lot of times my graph would come here, and my graph would come here. And my graph looks like a particular function at the end. So say for instance asymptote here may be x plus 2. Well, my graph here at this extreme over here would look like x plus 2. So x plus 2 would be my in behavior model. And on this extreme here would also look like x plus 2 at this extreme as well. So that would be my in behavior model. And so that's what we're looking at when we look at in behavior models. What does my graph look like at the extremes? Say for instance, if I had three x fifth plus 4x to the fourth plus 3x cubed plus 2x minus x plus 3. All right, this graph may look like something like this. Whereas this graph would look something like that.
Which graph would look like that?
Oh, I'm sorry. 3x to the fifth
Would be the dotted line?
would be the dotted line. Okay, this is my whole thing. So what would be my in behavior model? My in behavior would be the 3x to the fifth. On the left extreme, my graph behaves like 3x to the fifth. On my right extreme, my graph acts like 3x to the fifth. So that would be my in behavior model. A lot of times my leading term is my in behavior model. My in behavior model. And a lot of times I can find what my in behavior model, if we look at example 6 on page 73. If I look at 73, no, I want to change that. Let's go to 74, look at the box. If I look at my box, it says the function g is a right end behavior model if and only if, as x approaches infinity, f of x over g of x equals 1. Is my left end behavior model for f if and only if, as x approaches negative infinity, f of x over g of x equals 1. Okay? So, how do we want to look at that? Look at example 7. Finding in behavior models. Finding in behavior models. If I look at letter A, I'm going to take my leading terms. If I take my leading terms, 2x to the 5th over 3x squared. Let me write it down just for the people that are watching. So I'm just going to take my leading terms. I wrote that down wrong. This would be squared. There we go. Leading terms and simplify us. 2x to the 5th over 3x squared, which is equals to 2/3 x cubed. 2/3 x cubed would be a in behavior model. My graph would behave that way at the extremes. If I look at the next one, and we're going to look at this in just a second here. Look at the next one, g of x equals 2x cubed minus x squared, really doesn't matter what that is, plus x minus 1 over 5x cubed plus x squared. If I can remember more numbers at one time, it'd be better. Plus x minus 5. Again, if I take the leading terms, my highest degree terms, simplify, they cancel out, and 2/5 would be my in behavior models. And again, what do we say about limits? The limit as x approaches infinity, and the limit as I approach negative infinity, right? What's happening? Well, they're gonna look like my in behavior models. My in behavior model here is 2/5. That means this graph here at 2/5, the graph is going to look like that horizontal line at the extremes. The further out I get, yes, it's curving and curving and curving, but as farther out I get, it looks like a straight line the further out I get.
That's only if the f of x over g of x equals 1, right?
Well, this one is 2/5. But this one here, 2x to the 3rd,
Okay.
x to the 3rd looks like this. So that means my graph at the end would look like here and possibly here is what it would look like. We'll look at some examples in just a second. It may look like something like this. To do that. So if we get our calculators out, let me get my computer with my calculator.
I'm confused.
All right, we're going to clear it up in just a second here. TV here. Alright, so let's look at what we're talking about here. If we go down to number 8, let's look at x plus e to the negative x. So we would graph that x plus e to the negative x. And where's my x?
Are these like the quick review?
What's that?
Are these,
Finding end behavior models.
what page?
Page 74. Alright, and then type in x,
I wrote example
and then type in e to the negative x.
Cause those are different functions, like why?
They're all part of the same function, so I just split it up. So again, I got x plus e to the negative x, and I take the front part and you put here, and the back part and put here.
And graph.
Alright, and then we're gonna graph. Let me make my window. Do 10. 10. That way.
Interesting. Very interesting.
Alright, my blue. Well, I forgot what color is what. Let me go back.
Blue is the original function.
Blue is my original. Alright, my red is y equals x, and my e to the negative x is here. So as you look, as you see the blue, as I get closer and closer and closer to the extreme on the right, you see my blue line kind of merges into the red line, and you don't see the blue line anymore. So that means at the extreme, my end behavior on the right hand side, my right end behavior is acting like x. So my function x would be my right end behavior. If I take on the left hand side, you notice my black line is e to the negative x, and as I go to negative e to the x, I see that I get a left end behavior, because now the black line is merging into the blue. If I make my window bigger, you can see that the blue and the black are merging together. So e to the negative x would be my left end behavior, and x would be my right end behavior. Because you see here's the e to the negative x here, going back. Now according to what they said, what was the graph? X plus. My g of x is my end behavior, right end behavior, if this is going to equal 1. Well, let's look at this. Can you turn that back g of x, yes, so we have g of x equals x and h of x equals e to the negative x.
Okay.
Alright, so I divide by x. Okay, what do I get? I get 1 plus e to the negative x over x. Well, as my denominator gets bigger and bigger and bigger and bigger and bigger, what happens to my fraction?
It
It's
gets
smaller.
smaller.
It gets smaller, getting closer and closer and closer to
One.
Well, no,
0. So this is basically 0. 1 plus 0 is 1. So therefore that shows me that x is my right in behavior. Because f of x divided by g of x is 1. If I do it the other way around, the limit as x approaches negative infinity of x plus e to the negative x over e to the negative x. Alright, that's going to be the limit as x approaches negative infinity of x over e to the negative x plus 1. Well, what is e to the negative x? It looks like this. And as I get bigger and bigger, smaller and smaller and smaller, what's happening to my number? It's getting bigger. So what's happening to my denominator? If my e to the negative x is getting bigger, my denominator is getting bigger. As my denominator gets bigger, what's happening to my fraction?
Gets smaller.
It gets smaller, getting to 0. So therefore, this is 0 plus 1. So that means e to the negative x is my left in behavior according to the rules of the in behavior model. Now, when we do this, we can do it algebraically like we did here, or we can do it graphically like we did here on the board, one way or the other. All right? You're going to have to do it both ways. So take, for instance, if I go back to, did I erase it too soon?
Yeah, okay.
Sorry. If I go back to let's not do that one. Let's go do a simple one. F of x equals 3x squared plus 5. If I go back to here, as I said, my in behavior model is usually my leading term. So according to the definition, the limit as x approaches infinity of 3x squared plus 5 over 3x squared. Well, if I simplify this, the limit as x approaches infinity of 1 plus 5 over 3x squared. What's my right in behavior? Well, this is basically, as this x gets bigger and bigger and bigger, this fraction gets smaller, smaller, and smaller. This fraction is approaching 0 as far as out to the extreme I get, so I'm left with 1. So that means 3x squared is my right in behavior model. Okay? It would be the same way if I had it the other direction. I couldn't say 5. Because now that is going to be 3x squared over 5 plus 1. What happens to 3x squared over 5 as x gets bigger and bigger and bigger?
It gets bigger.
It gets bigger and bigger and bigger. So I don't have just 1, I have 1 with a big number. So 3x squared would also be my left in behavior as well. Now, in behaviors, what's happened is my in behaviors actually show me asymptotes. going back to this problem up here on the screen. My right in behavior was y equals x. I actually have an asymptote at y equals x on the right hand side. If I take this out. Take this out. Change my window back to
Using 10.
and I can see my graph, I actually have an asymptote at y equals x on my right end behavior. I actually have an asymptote at y equals e to the negative x. So my end behaviors, what I'm trying to get to is always show me my my asymptotes, whether it be horizontal, vertical, or horizontal or oblique.
So if it is like the 3x squared, because it was the right end behavior model, then it's going to be an asymptote.
There's going to be an asymptote on the right hand side.
Okay.
My graph will approach but never touch on the right hand side. If it's on the left hand side, it will approach and never touch.
I'm still confused. If you can figure out the right one, how do you figure out the left one?
The left one is going toward negative infinity.
Is it always going to be the same as the right one?
Sometimes it will be the same, sometimes it will not.
Like, how did we figure out that it was e to the negative x, other than they just told us?
Well, here's my graph. So I say, okay, let's look at what happens when I have right, so here's my first part, the x. And what does my graph on the right hand side look like?
Y equals x.
Y equals x. That's my right hand behavior. If I do it the other way, right, does my left part of the graph look like y equals x?
No.
No, so that's not a left end behavior. But if I do e to the negative x, what does my graph look like on the left hand side?
E to the negative x.
E to the negative x. So that's doing it graphically. The way we did it on the board earlier, that's the way we do it algebraically.
So you just take each term with a variable and see
Basically, somewhat, yes.
graph. Okay.
So let's look at
But the 5
y equals x squared plus sine x. Trying to find my right and left end behavior. So this would be the limit as x approaches infinity okay? What do we want to try? Well, let's try
X squared, right?
x squared. It'd be x squared over x squared plus sine x over x squared. Okay?
So that is one. That is the right hand because it's one plus something, and then when you
Well, I mean, it could be 1 plus something, but not.
Alright, well, let's think of sine x. What does sine x equal as x gets bigger and bigger and bigger?
one,
It always fluctuates between 1 and negative 1, right?
Oh, yeah.
What's happening to the denominator?
It's getting bigger.
It's getting bigger and bigger and bigger. So what's happening to the fraction? Sine x over x squared.
It's getting smaller.
It's getting smaller. So if we would look at, if we see that on the graph, do this here, do another one. Sine x.
Can you move the camera again?
Yeah, go ahead. Let's get rid of that. Get rid of that. Get rid of that. So here's my sine x over x squared. Alright, as I get bigger and bigger, what's happening to my sine x?
It's smaller.
Right. That's right, that's my sine x over x squared. So it's getting smaller as so it's getting closer and closer to 0. So this actually equals 1. So x squared is my right in behavior because I was going to positive infinity. If I would do this differently, now you can switch it back, Connor.
So this,
Some may say, okay, let's try sine x. Well, that's going to be the limit as x approaches negative infinity of x squared over sine x plus 1. Well, sine x is fluctuating between what?
-1 and 1.
Negative 1 and 1. X squared is doing what?
Getting bigger.
Getting bigger and bigger and bigger. So my fraction is getting
Bigger.
bigger and bigger and bigger. So this is not going to 0. So this is really 1 plus some big number. So that means sine x cannot be in my left end behavior. So therefore, I go back to x squared. The limit as x approaches negative infinity of 1 plus sine x over x squared. Well, sine x over x squared, what's it doing toward negative infinity?
Getting big.
Sine x
Closer
over
to
x,
0.
get closer to 0. So this is 0 plus 1, which is 1. So that means x squared would also be my left end behavior. Okay?
would there be a time where the left and behavior is not either of them? Like it's.
Could be, yes. Yes. Okay? So, let's look on page 76. It says use graphs and table to find the limit as x approaches infinity f of x and x approaches negative infinity f of x and identify all horizontal asymptotes. Okay? Sine 2x over x. Now remember, what does sine 2x over x look like?
It's equal,
Like that.
no.
So what's happening as I get closer and closer to infinity?
Are getting closer to each other.
Closer to 0.
Get closer and closer to 0.
Oh.
Okay? So, what's my limit as x approaches infinity of sine 2x over x? 0. What's my limit as x approaches negative infinity? 0. So therefore, what is my horizontal asymptote? Remember, if my right end behavior matches my left end behavior, then I have a horizontal asymptote. So therefore, my horizontal asymptote would be 0. My right hand limit was 0. My left hand limit was 0. So therefore, my horizontal asymptote here is y equals 0.
So, does that mean that all the points on the graph where it would equal 0, it doesn't?
Well, it's crossing the asymptote, but eventually it's gonna stop crossing.
Oh, okay.
Eventually, way down the line.
Oh, cause it would just be,
Correct. Because basically, you're gonna, once you stop bouncing like this, it's gonna look like a straight line, right there at 0. Look at number 4. 3x cubed minus x plus 1 over x plus 3. Alright, as I go to the right, what's happening to the numerator? Whoops. Sorry, Cam, sorry, Wendy. That was Connor's fault. Just kidding. What's happening to my numerator as my x gets bigger?
it's getting bigger.
It's getting bigger. What's happening to my denominator as x getting bigger?
It's getting bigger.
It's getting bigger. Okay? So therefore, which one's getting bigger faster?
Probably top.
The top, because it's x cubed, right? So therefore, what's happening to my fraction?
It's big.
Getting, no, smaller.
No, it's getting bigger.
It's getting bigger. Going toward infinity, right?
Yeah, sorry, I was thinking.
Infinity cubed is bigger than infinity.
Yeah.
Correct? So it's going toward infinity. On the left-hand side, where's it going? We got negative infinity cubed divided by negative infinity,
Oh, so it'll be going to infinity?
going to infinity as well. Do I have a horizontal asymptote?
No.
No, I do not. Let's look real quick. 2x minus 1 over absolute value of x. Now, if we notice here, we can take our leading terms and just use our leading terms. So 2x over absolute value of x. All right, if I simplify that, what do I get?
2.
2. All right? So as I get bigger and bigger and bigger, I get 2. As I get smaller and smaller and smaller, I get
2.
negative over a positive, which is a negative. So I'm actually going to be at
Negative.
-2. So on the right-hand side, I have an asymptote at 2. On the left-hand side, I have an asymptote at
Negative 2.
-2. So I have basically 2 asymptotes here. Okay? Because what my graph looks like, it looks like this. That's what my graph looks like. Okay? So we'll look at this some more tomorrow. All right?
Could you explain real quick how you can